Scattered. Sorry, guys. All right. So again, from research we've done, you know that the mean income of those living near the restaurant must be over $85,000 annually to support the type of upscale restaurant you wish to open. You decide to take a simple random sample of 50 people living near one potential location. Based on the mean income of this sample, you will decide whether to open the restaurant there. Right, so this is our context. First part of this question is state an appropriate null and alternative hypothesis, and be sure to define your parameter. Okay. So in this scenario, the value we have is the $85,000. The null hypothesis is that it will be equal to 85,000. The alternative, which is the thing we hope happens, is that it will be greater than 85,000. All right, so we have H naught, or H sub 0, is the mu average is equal to 85,000. Our alternative, H sub A, is that mu is greater than 85,000, where mu equals the mean income of all residents near the restaurant. Right? And so this last part is where we're actually defining the parameter. We're saying the parameter mu is what we're using, and this is the mean income of all residents, not the mean income of the people in the sample, right? For all residents, because that's our population. Is there anything I can clarify on this example, on this part? Right. Part B of this question, we want to describe a type 1 and type 2 error and explain the consequences of each. All right. So we have our two different types of errors. Type 1 is essentially when we reject the null hypothesis and say we have evidence for our alternative, and that's incorrect. Right? Suppose we reject it on accident, and then it's like, oops, that's actually true. Now we're in a predicament. Type 2 is if we fail to reject the null hypothesis when we should actually reject it. Right? And so how that turns out here is a type 1 error is finding convincing evidence that the mean income of all residents near the restaurant exceeds 85,000, when in reality it does not. So again, if we found convincing evidence of the alternative, that would mean that we rejected the null hypothesis. But the reality is that that was incorrect. A consequence of this would be opening a restaurant in a location where residents can't support it. And that would be the real life consequence of this type of error. So when they're asking about a consequence, that's what we're looking for. What's the real life thing that could happen if we make this type of error? Type 2, not finding convincing evidence that the mean income of all residents exceeds 85,000 when it actually does. So again, we collected our sample and somehow we did not find the evidence to reject the null hypothesis, so we failed to reject. We say we don't have evidence of the alternative, right? The consequence is that you will not open your restaurant in a location where residents could have supported it, and you lose potential income. Right, so when it's asking about the errors and consequences, think about what could actually happen. What would be a real life thing that would happen if that error was made? Is there any clarification I can give you guys? Anything I can explain better? All right. Excellent. Then we will move on. So we're gonna open up the next part, which is the first few slides here are just essentially review of notes and key concepts from yesterday's lesson, right? Some takeaways, right? So I encourage you to follow along on your own screen or view the shared screen. There we go. First, we have stating an appropriate hypothesis. This is an important part of what we're doing here. Right? In any significance test, the null hypothesis has the form H0 colon parameter equals value. The null hypothesis is the only one that gets an equal sign. Right? The value in the null hypothesis and the alternatives should all be the same. The alternative hypothesis has one of the forms, either alternative colon parameter less than value, parameter greater than value, or parameter not equal to value. Right, so we're either going to be hoping that it's less than the assumed value, greater than the assumed value, or just not the same as the assumed value. It could be greater, it could be less, but we're saying we don't think it's that. All right. We need to read the context carefully to determine the correct form of the alternative hypothesis. Hypotheses always refer to a population. Be sure to state the null hypothesis and alternative hypothesis in terms of population parameters. P, mu, sigma, right? We're using our population notations. Okay. Next, interpreting p-values. The probability that measures the strength of the evidence against a null hypothesis is called a p-value. The probability computed assuming the null hypothesis is true. So it's like a conditional probability, right? Given the null hypothesis is true, that the statistic would take a value as extreme as or more extreme than the one actually observed is called the p-value of the test. In other words, the probability of p hat, or sample, occurring assuming that the actual proportion is the true proportion is the p-value. Small p-values are evidence against H0. Large p-values fail to give convincing evidence against H0. If we have evidence against H0, we reject it. If we fail to have evidence against it, we fail to reject. When we're checking significance, right? When trying to determine significance, we can compare the p-value with a fixed value that we regard as decisive, called the significance level, written as alpha. When we use a fixed significance level to draw a conclusion in a significance test, we can use the following logic. If the p-value is less than alpha, we reject H0, and we have convincing evidence for the alternative. If the p-value is greater than or equal to alpha, so in that case we consider it large, we fail to reject the null hypothesis, and we do not have convincing evidence for the alternative. Okay. And so we need to have that p-value and a predetermined significance level to do this type of thing. But assuming we have those, this is how we can use that to reject or fail to reject the null hypothesis. And then we have our type 1 and type 2 errors, the two types of errors that can occur when doing a significance test. Right? If we reject the null hypothesis when the null hypothesis is actually true, we've committed a type 1 error. If we fail to reject the null hypothesis when the alternative is actually true, we have committed a type 2 error. And then we have our table that we saw yesterday, kind of highlighting how this works. Right, so our conclusion based on a sample, if we reject the null hypothesis, but it was supposed to be accepted, it was true. Right, we have a type 1. If we reject, and we should have rejected it because the alternative is true, correct? Right, fail to reject the null hypothesis, and the null hypothesis is true. That's correct, right? We fail to reject it, that means we have evidence to support it. We fail to reject it, however, the evidence should have shown us that it was false. Then we have a type 2 error. Right, so those are kind of like the key things that we need to like have an understanding of from section 9.1. Is there anything I can clarify about those things so far? then that brings us to our first question. So if you're following along on my screen, excellent. You can continue to do so, but please make sure to progress yourself up to the 6th slide here. And this is our first 2 questions. Okay. For each of the following settings, describe the parameter of interest and state appropriate hypotheses for a significance test. All right, so there's a few things I want to go over before we answer these. I'm going to, rather than me reading these out loud, I'm going to allow you guys to read these. However, do notice a couple things that you should have access to. On the bottom of your screen, you should have a student supports. There's a little bit of like hint or things to consider while constructing your answers there. You also do have the option, if it's easier for you to just write out a response on paper, take a picture of it, put that picture in the cloud, and upload that image. You can do that here if you like. That is now an option, right? You can upload an image. You may also need to use this math type entry. The way to get the notations that we want here, that you may want to have, for the null hypothesis, type capital H _0, right? And you get the underscore by saying shift and the like dash sign next to the plus or to the right of the 0, right? I can then say colon P equals some number. If I type it like this and then I highlight it and hit the type math, it switches it into nice notation. All right. And so and you only want to highlight the things that are math, right? If you highlight like actual typing, like a sentence, it's going to look really weird. Right. The other thing you may need, if you want to type mu, go \mu. That'll convert to your nice little mu Greek letter. Same thing if you end up needing alpha later. Right. If you need not equal to, that's \neq. Right. Greater than or equal to is \geq. Less than or equal to \leq. All right, so we can get all of these symbols if we need them. All right. If you need help, please let me know. So again, I'm going to give you guys some time here. We're going to give 5 minutes to start here to answer these 2 questions. If you have questions, concerns, comments, please put them in the chat or just shout out at me. I'm happy to help. Okay, guys, I know some of you are still working on both of these problems, and that's totally okay. What I'm going to do is look at the first question here. I know a lot of you guys are still on the first question. Some of you have moved on to the second one. So we're going to kind of quickly look at the first question and what the response could be. All right, so in this scenario, the assumed proportion is 85% or 0.85. Of the 85% of students get less than 8 hours of sleep. Janie wants to know if her classmates at her local high school, large high school, get that same proportion essentially, right? And if the same proportion of students have that amount of sleep. And so if you guys are looking at my shared screen, I have a possible solution up there. So we have the null hypothesis is P equaling 0.85. If you put 0.85, that's fine. And the alternative is that the proportion is just not 0.85. All right. And we get that it's just not equal to 0.85 because they're not interested in, is it less than 85%? Is it more than 85%? We just want to know if it's different. Is it not the same? And then we define where P is the true proportion of students at the large high school who sleep less than 8 hours per night. This last part, after what we've actually written as the hypotheses, is the definition of the parameter. We need that part. Is there any questions about this first question and how we've come up with the hypotheses and the definition? Definition. Okay. So then we need to do similar kind of ideas with the next question here, except this next question is not dealing with proportions. I'm going to tell you that it is dealing with means or averages. All right, so your parameter should be mu. Alrighty, everybody. We're going to talk about what the solution is for question number 2. And again, this is talking about the census, and in 2010 they had this marketing thing that said 10 questions in 10 minutes, that's all it takes. And so their claim is that it will take about 10 minutes to complete the census form, and we're suspicious and we think that it's going to take longer. Right, and so then we get the possible solution. Right, this is one way to write it. That the null hypothesis is that mu equals 10 minutes. The alternative is that mu is actually greater than 10 minutes. And mu is the true mean amount of time it takes to complete the census form. Right, it's important to say that mu is a mean, and that it does not represent the amount of time it takes. It represents the average or mean amount of time that it takes. That's an important distinction. If we were dealing with random variables and we said, hey, x, the random variable x represents the amount of time it takes people to complete the form, and it can take on multiple values, so to say, like our random variables can, that's one thing, but this mu represents the mean. So it's important to have in your definition. Just like when we define P, we're saying that it is a proportion. Okay. So anything I can clarify about these two problems? Any questions you have? Okay. We're going to move on to the next question. Once again, there are some student supports at the bottom of the screen there, if you want to look at that. This scenario, we have Simon reading the newspapers, claiming that 12% of all adults in the US are left-handed. This is the same context that we saw yesterday in one of our example problems. Right. He wonders if the proportion of lefties at his large community college is really 12%. Simon chooses an SRS of 100 students and records whether each student is right or left-handed. His hypotheses are stated below. The null hypothesis is that the proportion is actually 12%. The alternative is that it just is not 12%. It could be something more or less, where P is the true proportion of lefties at Simon's large community college. In his SRS, 16 of the students were left-handed, otherwise known as 16% or 0.16. A significance test yields a p-value of 0.2184. What conclusion would you make if alpha equals 0.1? Justify your answer. So in this case, you might want to refer back to screen 4. That allows us to make a conclusion based on a significance level. We then need to make sure to write our conclusion based on the given context. Right. And again, if you like, you're welcome to write your response by hand, take a picture, upload that. And you also do have your little math type editor if you need to use that. Alrighty, okay, we're going to talk about this one. I see a lot of good work in here, guys. and this is why we're doing these kind of practice problems, because the verbiage and the language and how we're supposed to actually answer these questions can be very confusing, because there's lots of different things we can say about this data. So if you look at the shared screen, there is a solution here now. So because the p-value of 0.2184 is greater than alpha of 0.1, we fail to reject the null hypothesis. We have a large p-value. This means we do not have convincing evidence that the proportion of left-handed students at Simon's College is different from the national proportion. Okay, notice that I didn't say we fail to reject H0 and we do not have convincing evidence for HA. I said we do not have convincing evidence of what we were trying to show. We were trying to show that the proportion of lefties at Simon's College is different. Unfortunately, we don't have convincing evidence to support that. Right. So our answer provides the context of the question. What were we trying to show? That because of our evidence, we cannot, or it could be that we could show. Okay. What questions do you guys have? What can I clarify? How can I help?
Mr. Mosley.
Mm-hmm.
When you stated the Simon's College is different from the national proportion, do you have to state the sample and then the population, like results? Or
as far as like, do I need to refer to the size of my sample and or something like that? Or no, not in this case. So when we're interpreting the p-value, it's appropriate to cite the size of the sample and things like that. Like if I were just saying, what does the p-value of 0.2184 mean? What does it represent in this context? Then I would have a statement that's more along the lines of, you know, there's a 21.84% chance of getting a result of 16 students out of 100 or more, right? Based on the assumed actual proportion of 12% when we sample from an SRS of 100 students at the school. So in that case, when I'm interpreting the p-value, I'm going to state those kind of things. But with this type of answer, I'm only saying like I don't have evidence to support my alternative. And so I'm stating what the alternative is in context. And the alternative was that the proportion of left-handed students is different from the national proportion.
Okay, thank you.
Mm-hmm. You're welcome. Is there anything else I can clarify? Okay. All right, let's move on. And in this case, now we are interpreting our p-value. However, we're trying to decide what is wrong with the student's explanation. So when asked to explain the p-value in the previous exercises, lefties, a student says there is about a 22% chance that the null hypothesis is true. Explain why the student's explanation is wrong. Why is this not an appropriate explanation? Okay, let's talk about this one. So there's a few different ways we can answer this question. I'm going to provide one of those possibilities here on the shared screen. It is kind of this is the short and sweet answer. And then there's a longer answer. So one of the reasonings is here, either the null hypothesis is true or it is false, right? It isn't true some of the time and not true other times, which means there's not a probability of it being true or false. That's not a thing. It either is true or it isn't, right? And so that's part of why this is wrong, right? The probability, that 22% chance, applies to the probability of getting that result based on the assumption that the null hypothesis is true. Right, so in this context, it would be like a correct thing to say in interpreting the p-value or explaining the p-value would be like assuming the true lefties is 12%. There is about 22% chance of at least 16 students out of an SRS of 100 I'm in school being left-handed. That's all of it. All right, so this would be a correct interpretation, like if we're fixing this, right? Assuming that the true proportion of lefties is 12%, then there's about a 22% chance of at least 16 students out of an SRS of 100 at Simon's school being left-handed. So if we repeated this process over and over again, selecting SRSs of 100 students, we'd have about a 22% chance of getting 16 or more students who are left-handed, assuming that the true proportion is 12%. That's what our p-value is. It says if I take this SRS over and over again, this is the probability of me getting this result or something more extreme than that result, which in this case would be greater than. Okay. Is there anything I can clarify? Do you have any questions? Okay. All right, we're going to move it on. We're actually going to skip this next question and go to the final two questions here, which is all multiple choice on the final two. Just going to open this bad boy up. And please go to the 10th slide. So skip the blood pressure one and go to mice in a maze. Right, so this is a single multiple choice. The next screen has a lot of multiple choice. There's 3 different multiple choice questions on that one. And I have a typo, of course. So experiments on learning in animals sometimes measure how long it takes mice to find their way through a maze. The mean time is 18 seconds. Right, for one particular maze, a researcher thinks that a loud noise will cause the mice to complete the maze faster. Right, she measures how long each of 10 mice take with noise as a stimulus. The appropriate hypotheses for the significance test are. So in this case, please select what you believe are the 2 appropriate hypotheses for the null hypothesis and the alternative. Right, that's that question. The next one, there's 3 multiple choice questions attached to this same original context here in the top left. Right, there's a city council. They want to know if a majority of city residents support a 1% increase in sales tax to fund road repairs. To investigate, they survey a random sample of 300 city residents and use the results to test the following hypotheses. The null hypothesis is that the proportion is 50%, right, 5.5. The alternative is that they essentially have the majority support they need, and more than 50% will approve this. All right, will support the increase. All right, and again, we define where P is the proportion of all city residents who support a 1% increase in the sales tax to fund road repairs. All right, we have a question about a type 1 error in this context, how that would occur. We have a given p-value, right? Or not a p-value. Sorry, that's not a p-value. We do have a p-value and results. In the sample, we have 158 out of 300 who support the increase. We get a p-value of 0.18. What's the correct interpretation of the p-value? And then based on the p-value, 0.18, which of the following would be the most appropriate conclusion? Right, so we've got 4 multiple choice questions essentially to work through. All right, guys, here we go. We're going to go over these last few problems here. So if you like, please follow along. You can look at the shared screen or just follow along on your own screen, but we're going to first look at the mice in a maze problem. Right, based on this context, our value will be 18 or 18 seconds. Right, we're dealing with average, right, and so that means that we're going to be dealing with mu as a parameter, not x bar. X bar is the sample. We do not deal in statistics, sample statistics when we're doing this, right? And so mu will be equal to 18 for our null hypothesis, and we think it will be less than 18 for the alternative. So the fourth option there, h sub 0 mu equals 18, h sub a mu is less than 18, are our two hypotheses. Because if they're going through the maze faster, they're doing it in less than 18 seconds. All right. Now here, a type 1 error in the context of this study occurs if the city council, right? So remember, a type 1 error, we look back at our screen 5, type 1 is when we reject the null hypothesis when it should be considered true, which means we would say that there's support, more than 50% of the people support this tax increase, when in reality, we don't have that evidence. Right? And so that would be our second statement. Right? We have that this error would say that we found convincing evidence that a majority of residents support the tax increase, when in reality, at most 50% of the city residents support the increase, because this last part of the second part of the phrase here refers to our null hypothesis being true, saying at most 50%, right? The second one here in the sample, right? We want to know what the correct interpretation of the p-value is. Right? This ends up being the third option here, assuming that 50% of the residents support the tax increase. There's an 18% probability that the sample proportion would be 0.527 or higher by chance alone. And we could also include in this description, as Jose brought up earlier, we could add that the sample proportion would be 0.527 or higher by chance alone in a random sample of 300 residents from this community, from this city. Last one here, which of the following would be the most appropriate conclusion based on our p-value? Right. This ends up being, we have a large p-value. When p-value is large, we fail to reject h naught. Right, so we get to exclude that we reject h naught. We're failing to reject, and we do not have convincing evidence that more than 50% of the city residents support the tax increase. Right, we do not have evidence of our alternative. Right. Is there anything I can clarify? Any questions, comments? Right. Alrighty, so that is the end of the activity. The module for Chapter 9 is still under construction here. I've got a lot of it built out. I'm working on the practice problems for Section 9.1 right now in between classes. It should be ready soon. I do have the study guide for Section 9.1 and the resources for 9.1 from the book, and most of the resources for 9.2 and 9.3 from the book and from AP Daily and things like that. So if you want to take a look at the resources, please do so. I should have the study guide for 9.2 and 9.3 up later this week, along with practice problems and such, like I normally do. Other than that, if you have any questions, if you need support on what we're covering right now or previous lessons or assessments, please let me know. Send me a message. You can stick around right now after this call and ask. Just make sure you ask for the help you need. Besides that, we are done for today. Have a wonderful rest of your day, and I should see you guys next week.